You see a fuzzy patch through your telescope, 4 inches of glass. Magnitude 17.8, your hands shake. You stack 20 frames, 30 seconds each. 10 minutes later, the computer shows you something impossible. A visitor from another star system. July 4th, 2025. Vamshi Kesareddy in the United States just changed amateur astronomy forever. 3. iAtlas appeared on his screen not because he had the biggest telescope or the darkest sky. He had software, image stacking. The technique that professional surveys dismissed as too slow now beats the old visual hunters at their own game. And this comet from beyond our solar system reveals something nobody expected. Let's talk about what happens when the rules flip. You sweep the sky in vertical strips, lawnmower pattern, 1 to 5 seconds per field. Your eye adapts to darkness for an hour. You memorize star patterns. Deep Sky Stacker never existed, neither did computers powerful enough to process images while you watched. William Bradfield in Australia found 18 comets between 1972 and 2004 using an 8-inch reflector and his eyes. 400 hours of hunting per discovery on average. Raw vision, raw patience. The human eye sees faint objects better using averted vision, looking slightly to the side. Every comet hunter knew this. The trick worked because rod cells in your peripheral vision detect motion and faint light better than the cone cells in your center. But rod cells cannot distinguish color or fine detail. You'd glimpse something. Maybe. Check your charts, sweep back, still there. Probably a comet, probably not a galaxy you forgot. This method dominated for 2 centuries. Charles Messier cataloged deep sky objects in 1771 specifically because he kept mistaking them for comets. The confusion itself tells you how hard visual hunting was. Messier's catalog became the backbone of amateur astronomy, but it started as a list of things that weren't comets. If you value documented astronomical discovery and technological revolution like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Auburn University Physics Department's paper published October 8, 2025, in Physical Review Analyzing Swift Observatory Data, and Martin Cordner's August 28, 2025, preprint paper from NASA. Goddard Space Flight Center, detailing JWST spectroscopic observations that reveal the 8-to-1 carbon dioxide to water ratio, the highest ever recorded in any comet by 6 standard deviations. These aren't popular science articles. These are the actual research papers from the teams operating the instruments. Now back to the information. Signal remains constant. The math works like this. Stack 4 images, and the signal-to-noise ratio improves by a factor of 2, the square root of 4. Stack 16 images, and you get a 4-fold improvement. Stack 100 images, and the improvement reaches 10-fold. This isn't theory. This is physics. Every astrophotographer who's ever processed a deep sky image knows the rule. More frames equals cleaner image. The technique emerged from speckle interferometry in the 1970s. David Fried at the Optical Sciences Company showed that atmospheric turbulence created random patterns in telescope images. By taking many short exposures and processing them together, you could reconstruct detail that single long exposures blurred away. Amateur astronomers adopted the method slowly. Early software required Unix workstations. Processing took hours or days. By 2011, free programs like Deep Sky Stacker ran on home computers. The revolution happened quietly. No press releases, no announcements. Just thousands of amateurs suddenly seeing objects their telescopes shouldn't be able to resolve. 4 robotic telescopes scanning for potentially hazardous asteroids. The system processes images automatically, comparing each frame to star catalogs, flagging anything that moves. A human reviews the detections. Larry Deneau at the University of Hawaii saw it first. Garden variety, near-Earth object, he thought. By morning, follow-up observations from dozens of telescopes worldwide confirmed something else. Hyperbolic trajectory, not bound to our sun, not from here. The Minor Planet Center assigned the designation 3I/Atlas on July 2nd. Third interstellar object confirmed. First letter I for interstellar. Atlas for the survey that found it. 1I/Oumuamua in October 2017. 2I/Borisov in August 2019. Now 3I/Atlas. The naming convention tells a story. We're finding these objects now because we're looking harder and processing faster. Here's what matters. The comet was already active, already bright. At 6.4 astronomical units from the Sun in May, TESS, the transiting exoplanet survey satellite, recorded it glowing. Water ice doesn't sublimate much that far out. Most solar system comets remain quiet beyond 5 AU. 3I/Atlas was already venting gas at a distance where it should be frozen solid. This told astronomers immediately that something exotic lived inside this nucleus. Carbon dioxide ice, or carbon monoxide, volatiles that sublimate at temperatures water ice laughs at. The test detection used shift stacking, moving target, fast proper motion. You can't just stack images normally because the comet moves between frames. The software shifts each image to account for the comet's motion, then stacks. Stars become streaks. Comet becomes clear. The technique revealed Three-Eye Atlas 2 months before official discovery. Not because anyone was looking for it, because researchers went back through archived data after the discovery and applied new processing methods. The past contains objects we haven't found yet. We just need better software. Citizen scientists with Unistellar smart telescopes joined the hunt immediately. Vamshi Kesareddy in the United States captured Three-Eye Atlas on July 4th at magnitude 17.8, 3 to 4.5 inch apertures, small telescopes, the kind you can carry in one hand. Unistellar instruments automatically stack images in real time. Point at a target. The telescope aligns itself using star patterns. Built-in camera captures dozens of exposures. Internal processor stacks them live. The screen shows you a clean image within minutes. No computer required. No processing skills needed. 26 observers contributed data across 22 hours of continuous coverage. Unprecedented for ground-based amateur work. Dr. Ariel Graykowski at the SETI Institute measured brightness from these observations. 17.8 magnitude. Possibly the faintest object the unistellar network ever successfully detected. This matters because professional telescopes with meters of aperture couldn't do better. The stacking technique compensated for small aperture. More frames multiplied the light gathering ability. The network proved that distributed amateur telescopes using image processing can compete with centralized professional facilities. Not in every task. But in time-domain astronomy, where you need continuous coverage and fast response, amateurs now hold the advantage. Traditional visual hunting demands dark skies. Light pollution kills faint objects. Your eye can only adapt so far, but stacked images pull signal from beneath the noise floor. A single 30-second exposure from a light-polluted backyard shows almost nothing. Stack 20 of those exposures and structure emerges. Stack 100 and you're seeing objects invisible to the human eye even from pristine dark sites. The technique doesn't violate physics, it just uses statistics. Every photon from the target hits your sensor in the same position across multiple frames. Photons from light pollution, sky glow, and electronic noise hit random positions. Stack enough frames and the random sources average towards zero while the consistent signal multiplies. Simeon Schmaus processed a new image of Three-Eye Atlas using 20 stacked 30-second exposures. 8th magnitude glow, faint but clear. Diffuse coma visible. The comet sat 30 million kilometers from Mars at the time. Small nucleus, up to 5.6 kilometers across. Receiving only 40% of the sunlight Earth gets, yet visible in stacked frames from small amateur telescopes. This is the new reality. You don't need dark skies anymore, you need patience and processing power. The Hubble Space Telescope imaged Three-Eye Atlas on July 21st, 2025, 277 million miles from Earth. Wide field camera captured the teardrop-shaped dust cocoon streaming from the nucleus. Hubble tracked the comet's motion, so background stars appeared as streaks in the exposure. This is standard practice for fast-moving targets. You track the object, not the stars. The image revealed the coma spanning 26,400 by 24,700 kilometers. Twice Earth's diameter, an elliptical cloud of gas and dust. The nucleus itself remained unresolved. Too small, too far, too dim compared to the surrounding coma. Upper limit on diameter estimated at 5.6 kilometers. Could be as small as 440 meters. The uncertainty tells you how hard these measurements are. Hubble observations, as of August 20th, 2025, constrained the size but couldn't nail it down. The coma's brightness accounted for most of the object's apparent magnitude. This suggests a small nucleus with high activity. More like 2I Borisov than 1I Oumuamua. Borisov measured less than 1 kilometer across and vented prodigiously. Oumuamua showed no coma at all, leading to speculation it wasn't a comet. Three-Eye Atlas clearly behaves like a comet. Active, outgassing, leaving a trail. James Webb Space Telescope observed Three-Eye Atlas on August 6, 2025. NIR spec infrared camera, spectrograph mode. The instrument split the comet's light into constituent wavelengths, revealing chemical fingerprints. Martin Cordner at NASA Goddard led the analysis. Catholic University of America co-author. The paper appeared on Archive August 28th as preprint 2 508.18209. Not published yet, pre-peer review. But the data came from JWST, and the team knows what they're doing. The spectrum showed carbon dioxide dominating, water present, carbon monoxide present, carbonyl sulfide tentatively detected. Nothing shocking there. All expected in a comet's coma. Then came the ratios. Carbon dioxide to water 8:1, highest ever observed in a comet. 6 standard deviations above the typical value for long period and Jupiter family comets. Standard deviation measures how far from normal something sits. 1 standard deviation is common variation. 2 is unusual. 3 is rare. 6 is borderline impossible if this comet formed the same way as solar system comets. But 3I Atlas didn't form here. It formed somewhere else, around another star, in conditions we can only guess at. Consistent with previous observations of other comets. This creates a puzzle. Why is carbon dioxide enriched so heavily while carbon monoxide behaves normally? 3 explanations appeared in the Cordner paper. First, intrinsically carbon dioxide-rich nucleus. The comet formed close to the carbon dioxide ice line in its parent protoplanetary disk. The ice line marks the distance from a star where a specific volatile can condense into solid form. Closer than the line, the molecule stays gaseous. Farther out, it freezes. Our solar system has multiple ice lines. Water ice line sits around 5 AU from the Sun. Carbon dioxide ice line sits farther out, where temperatures drop enough for carbon dioxide to freeze. If 3I Atlas formed in a region rich in carbon dioxide ice, its nucleus would naturally contain more carbon dioxide than water. Second explanation involves radiation. Interstellar space bombards objects with cosmic rays, high-energy particles. Over millions or billions of years, radiation processes the surface ices, creating new molecules. Carbon dioxide could form from carbon monoxide and oxygen in the ice matrix, driven by radiation chemistry. Solar system comets spend most of their time in the Oort cloud, or Kuiper belt, protected somewhat by the Sun's heliosphere. 3. I Atlas drifted through true interstellar space with no such protection. The radiation dose could be orders of magnitude higher. Third explanation focuses on thermal properties. If heat from the Sun penetrates the nucleus slowly, carbon dioxide with its lower sublimation temperature would vent first. Water ice, deeper in the nucleus, waits for higher temperatures. The lopsided ratio reflects not the nucleus composition, but the venting sequence. As 3I Atlas approaches perihelion, water production might increase dramatically, bringing the ratio back toward normal values. Observations in December 2025, after the comet emerges from solar conjunction, could test this hypothesis. 3I Atlas showed greater than 77 as a 3 sigma lower limit, formally consistent. This suggests the material formed in an environment with similar carbon chemistry to our own solar system, not radically alien. The parent star probably had metallicity within a factor of 2 of the Sun. Thick disk population. Older stars with lower heavy element abundance than young disk stars, but not as depleted as halo stars. The comet's galactic velocity supports this. U equals negative 51 kilometers per second. Velocity away from the galactic center relative to the Sun. W equals positive 18.5 kilometers per second. Velocity upward through the galactic plane. The high W velocity indicates a tilted orbit around the Milky Way. Thick disk or thin disk membership, not halo. The parent star might be 10 billion years old, twice the Sun's age. The comet could have formed 10 billion years ago, been ejected shortly after, and drifted through the galaxy ever since. A time capsule from the early epoch of planet formation. The carbon isotopes tell us the chemistry then wasn't radically different from now. Swift's 30-centimeter telescope operates above Earth's atmosphere, free from ultraviolet absorption. Dennis Bodowitz at Auburn University led the observations, published October 8, 2025 in Physical Review. 2 visits in July and August. Each observation combined dozens of 3-minute exposures. Total integration, 42 minutes in visible light, 2.3 hours in ultraviolet. Patience, stacking. Same technique at space telescope scale. The hydroxyl signal emerged from 40 kilograms per second of water vapor leaving the nucleus, roughly 2.5 tons per minute. Fire hose at full blast. Except 3I Atlas sat nearly 3 times farther from the Sun than Earth when Swift detected this. 2.8 AU in August observations. Most comets don't produce significant water vapor beyond 2 AU. Something else drives the activity. Small icy grains ejected from the nucleus. Sunlight heats them directly. They sublimate in the coma rather than on the nucleus surface. This extended source mechanism appears in only a handful of distant comets. Complex layered ices, clues to formation conditions. Multispectral observations. Resolved the coma, rich in carbon dioxide and water. No tails or jets visible at that time. The coma extended to a 23-kilometer radius, small compared to later observations. Production rates high relative to the nucleus size. If the nucleus measures 1 kilometer across, it's venting gas at rates that should deplete the surface quickly. This implies either a very icy composition or active venting from discrete sources on the nucleus. Comets often have active regions where jets emerge. These regions receive more sunlight or have thinner dust mantles. The rest of the nucleus remains dormant. 3I Atlas might concentrate its activity in a few bright spots. SphereX data supported the carbon dioxide dominance JWST found. Independent confirmation using different instruments strengthens the conclusion. This comet really is carbon dioxide rich, not an instrumental artifact, not a processing error, real. Closest approach to Mars occurred that day, 30 million kilometers separation. Cass's camera, color and stereo surface imaging system, designed to photograph Martian terrain, pointed at a comet instead. The image showed a faint hazy glow, coma visible but nucleus unresolved, less than 1 pixel. Expected. The camera sits at Mars orbital distance, the comet 30 million clicks away. Mars Express also observed with HRSC, high-resolution stereo camera, and spectrometers, Omega and SpyCam. Whether the spectra showed enough signal to characterize composition remains uncertain. The comet's brightness determines whether you can spread the light across wavelengths and still detect anything. Mars-based observations offered a unique geometry, different viewing angle than Earth-based instruments, different illumination conditions. The data helps constrain models of coma shape and activity distribution across the nucleus surface. Combining observations from multiple spacecraft at different locations triangulates the three-dimensional structure of the coma. Too small, too far, too faint. Social media images claiming to show Perseverance photos of the comet turned out to be misidentified. The rover's cameras resolve rocks meters away, not comets 30 million kilometers distant, but the false images spread widely. People wanted to see an interstellar visitor photographed from Mars. The desire made the fake seem plausible. This happens with every major astronomical event. Doctored images, misattributed photos, honest mistakes compounded by viral sharing. The real science takes longer. Real images require patience. Real analysis demands caution. But real results deliver substance the fakes never approach. Weather satellites orbit Earth, watching cloud patterns and storms. They also see comets passing near the sun. Solar conjunction means the comet passed behind the sun from Earth's perspective. Ground-based telescopes couldn't observe, too close to solar glare. But a satellite positioned correctly could catch a glimpse. GOES, 19 did. Images pending analysis. Solar conjunction lasted roughly 2 months. 3I Atlas reached perihelion on October 29th, 31st. Sources vary slightly depending on orbital refinement. 1.36 AU from the Sun, between Earth's orbit and Mars's orbit, closer to Mars. The comet's hyperbolic trajectory swung it around the Sun's gravity well and back out toward interstellar space. Not captured, not bound, never returning. One visit, one chance to observe. And because we caught it inbound, not outbound like Oumuamua, we had months to study it. Multiple instruments, multiple wavelengths, ground-based, Mars-based, space-based, optical, infrared, ultraviolet, radio. The Allen Telescope Array at the SETI Institute targeted 3I Atlas on July 2nd, 2025, looking for narrowband radio emissions, artificial signals, SETI work. Dr. Wael Farah led the observations. They found natural radio emissions consistent with cometary outgassing. No technosignatures, no alien spacecraft, just a comet. The search itself matters. Every interstellar object gets checked. 1, Oumuamua got checked. 2, Borisov got checked. 3, Atlas got checked. Someday, we might find something that checks different. This time, nature. Gemini South Telescope in Chile captured near-infrared spectra on July 5th and 14th, 2025. Water ice detected. First confirmation of water in the coma. NASA Infrared Telescope Facility in Hawaii added observations. Multi-object spectrograph on Gemini North provided visible light spectra. The comet's coma appeared clear, teardrop shape, tail forming, dust streaming away from the sun. Gemini images showed tens of thousands of kilometers of tail extension. Faint, requires processing, but visible. The dust tail reflects sunlight. Type 2 tail in comet classification. Dust particles pushed by radiation pressure. Type 1 tails are ion tails, gas ionized by solar wind and dragged along magnetic field lines. 3, Atlas displayed both types at different times. Dust dominated early observations. Gas became more prominent as the comet warmed approaching perihelion. Monitoring these changes reveals how the nucleus responds to solar heating. 4 8-meter mirrors working together, X-shooter spectrograph, visible and near-infrared coverage. The spectrum revealed cyanide gas, CN, and atomic nickel vapor. Nickel usually appears alongside iron when metallic compounds sublimate from comets. 3I Atlas showed high nickel abundance. The team suggested nickel tetracarbonyl as the source. Highly volatile molecule. Breaks apart under ultraviolet light, releasing nickel and carbon monoxide. This could explain the high activity at large heliocentric distance. Nickel tetracarbonyl sublimates at very low temperatures. Far from the sun, this molecule would vent while water ice remained frozen. As the comet approached the sun, ultraviolet radiation increased, breaking more nickel tetracarbonyl molecules, releasing more nickel into the coma. The detection method required ultra-sensitive spectroscopy. Nickel emission lines are faint. You need large aperture, long exposure, and careful calibration. The Very Large Telescope delivered all three. Amateur telescopes cannot detect nickel vapor. Some observations remain beyond reach of distributed networks. Professional instruments still dominate certain measurements. High-resolution imaging revealed the coma spanning 26,400 by 24,700 kilometers. Elliptical, slightly elongated. This asymmetry suggests uneven outgassing, more activity on one side of the nucleus than the other, or preferential dust ejection along specific directions. Comets rotate. As they spin, active regions face the sun at different times. This creates day-night cycles in outgassing, producing jets and coma asymmetries. 3I Atlas rotates with unknown period. Nobody has measured it yet. The rotation period determines how fast the nucleus spins, which affects heat distribution and activity patterns. Future observations after solar conjunction might constrain the rotation using coma brightness variations. Vera Rubin Observatory serendipitously imaged 3I Atlas during science validation from June 21st to July 3rd, 2025. Brand new facility, not yet fully operational, testing systems. Happened to point at the right patch of sky. The images showed slight coma diameter increase over those 2 weeks, growth consistent with approaching solar heating. The observations also constrained nucleus diameter. Upper limit tightened. Rubin would have discovered 3I Atlas if science validation had started 2 weeks earlier. A reminder that survey capability depends on when you look, not just how well. Rubin Observatory begins full operation soon. Legacy Survey of Space and Time, LSST, 10 years of nightly sky coverage. Every 3 days, the entire visible sky. Fast-moving objects, transients, variables, asteroids. Comets, interstellar visitors. Projections estimate dozens to hundreds of interstellar objects detected during LSST operations. Some will be asteroids like Oumuamua, some will be comets like Borisov and 3I Atlas. Some might be something else entirely. The statistics will improve from 3 objects over 8 years to potentially 50 objects over 10 years. We'll learn whether these visitors are common or rare. We'll sample diverse compositions. We'll see if 3I Atlas's carbon dioxide enrichment is typical or exceptional. The answers wait in data not yet collected. Rubin represents the future of survey astronomy. Wide field, fast cadence, automated processing, immediate alerts. Amateur astronomers with stacking software and professional surveys with robotic telescopes are converging on the same capability. Finding things fast. AutoStacker followed, refining the lucky imaging approach for solar system targets. Cyril offered Linux compatibility. PixInsight provided professional-grade tools for serious amateurs willing to pay. Each program implemented the same core concept differently. Align images, combine images. Reduce noise. The implementation details varied. Registration algorithms differed. Some used star triangles. Some used cross-correlation. Some offered local alignment to account for atmospheric distortion across the field. The output quality varied too. But every program improved on single-frame images. By orders of magnitude sometimes. The transformation felt like switching from film to digital, except this happened within digital imaging, from single digital frames to stacked digital frames, another quantum leap in capability. The human eye integrates light over roughly 1/10 of a second. Your brain processes the resulting signal. No memory carries over between integration periods. You cannot consciously stack images. Your visual system doesn't work that way. Digital sensors integrate light over exposure time you control. Seconds, minutes, hours. Then the data sits in memory, perfect recall. Stack as many frames as you want. The sensor doesn't fatigue, the stars don't move, or they do predictably, and you correct for it. Image stacking exploits these advantages: infinite patience, perfect alignment, statistical averaging. 3 tools the human visual system lacks. William Bradfield couldn't stack his retinal images. He relied on memory, star charts, and luck. When he found a comet, it appeared because his eyes adapted. His experience guided him, and the comet happened to be bright enough and positioned correctly. Image stacking shifts the threshold. objects too faint for any human eye become accessible to a 4-inch telescope with a webcam. Vamshi Kesareddy detected magnitude 17.8. No human has ever seen something that faint, unaided, not even close. Magnitude 6 is the naked eye limit under perfect conditions. Magnitude 17.8 is over 60,000 times fainter. You need instrumentation. You need processing, you need time, but you don't need a giant telescope anymore. Precise astrometry still needs careful calibration. Some measurements remain hard, others become easy. The balance shifts. 3, iAtlas demonstrates the new balance. Discovery by robotic survey, follow-up by citizen scientists, detailed characterization by professional facilities. Each group contributes what it does best. Atlas scans the entire sky every night. Impossible for humans. Unistellar observers provide continuous monitoring. Impossible for professionals with limited telescope time. JWST and Hubble deliver precision spectra and imaging. Impossible for amateurs. The ecosystem works because each component plays its role. No single entity could accomplish what the combined effort achieved. The comet emerges from solar conjunction in late November. Morning sky, constellation Virgo, magnitude 10.5 predicted. Reachable by amateur telescopes. 6-inch reflector with stacking should resolve it. Larger instruments will see it clearly. The brightness depends on activity level. If the comet undergoes an outburst, it brightens. If activity declines, it fades. Comets are unpredictable. 2, I Borisov, fragmented slightly. Oumuamua remained inert. 3, iAtlas could do anything. The December observations will measure the carbon dioxide to water ratio again. If it changed, that tells us about nucleus composition and thermal properties. If it stayed constant at 8:1, that supports the intrinsically carbon dioxide-rich hypothesis. Either result teaches us something. By January 2026, 3i-Atlas will be too faint to observe even with Hubble. The visitor departs, back to the interstellar void. Galactic orbit resumes. 8,000 years or 8 million years from now, it might encounter another star system. Maybe someone there will discover it inbound and study it the way we did. Or maybe it will pass unnoticed through empty space forever. We found this object because Atlas happened to be operating, because Larry Deno reviewed the data that night, because follow-up observations confirmed the trajectory quickly, because dozens of teams pointed their instruments at it immediately. If discovery had occurred 2 months later, 3i-Atlas would have been inbound toward perihelion already, closer to the sun, harder to observe. If discovery had occurred 2 months earlier, it would have been fainter, harder to confirm. The timing mattered. Luck played a role. Preparedness played a bigger role. The surveys exist because we decided to build them. The follow-up instruments exist because we decided to fund them. The amateur networks exist because companies built accessible telescopes and software made processing trivial. None of this was inevitable. All of it was chosen. We built a system capable of finding interstellar visitors. The system worked. 3i-Atlas rewarded that effort with data. This comet formed in conditions very different from the comets we know. Or it experienced processing we don't understand. The radiation hypothesis is testable. Measure more interstellar comets. If they all show similar enrichment, radiation processing is likely. If 3i-Atlas is unique, formation conditions are likely. We need more data. The Cordner paper emphasizes this. 1 object is a discovery. 3 objects is a pattern. 10 objects is a dataset. 50 objects is statistics. We're at 3 interstellar objects confirmed. 47 to go for real statistics. Rubin Observatory will get us there, maybe within a decade, maybe sooner if we're lucky. Every new detection refines our understanding. Every measurement tests hypotheses. The scientific method proceeds 1 observation at a time. Patience and thoroughness beat speculation every time. This script is researched and factual, using sources from the SETI Institute's July 2nd, 2025. Broadcast featuring Dr. James Davenport from University of Washington, Dr. Ariel Grakowski from the SETI Institute, and Dr. Stockter. Whale Farah analyzing 3i-Atlas discovery in the August 28th, 2025, Archive preprint by M.A. Cordner detailing JWST observations published as Paper 2508.18209 that showed carbon dioxide to water mixing ratio of 7.6 plus or minus 0.3, quantified as 6.1 sigma above the trend line for long period in Jupiter family. Comets when excluding the hypervolatile rich outlier C/2016 R2. These are primary sources from the observing teams. Now back to the information. A single photon hitting your sensor tells you almost nothing. Which direction did it come from? What wavelength is it? 1 photon doesn't answer these questions well. But 1 million photons from the same source build a picture. The source's spectrum emerges, its brightness stabilizes. Its position becomes clear. Collecting those million photons takes time. Visual observers collect photons for 1/10 of a second at a time. Their million photons arrive piecemeal, never accumulating into a coherent data set. Stacking observers collect photons for minutes or hours, storing every bit of data, then processing it together. The million photons accumulate, the picture emerges, information wins over noise. This is why stacking beats visual hunting for faint objects, not because the telescope is better. Because the data handling is better. Time becomes weaponized. Every second of exposure adds signal. Every frame stacked multiplies the advantage. Traditional hunters needed to see the comet in real time. Modern hunters need only to record data. The seeing happens later, in software, when time compresses and patterns emerge. He pointed his telescope at coordinates provided by the SETI Institute and recorded data. The telescope and software did the hunting. He provided the aperture and the time. The machine provided the eyes. This represents a philosophical shift. Astronomy began as a human activity, eyes on sky. Drawing what you see. Photography automated the recording. Digital imaging automated the storage. Stacking automates the accumulation. At what point does the human become optional? Not yet. Someone still chooses where to point the telescope. Someone still decides what data to collect. Someone still interprets the results. But the line between astronomer and instrument blurs. Citizen scientists contribute observations without necessarily understanding the underlying physics. The data goes to professional astronomers who analyze it. The loop works. But the citizen scientist's role changed from observer to data collector. Not worse, different. The old visual hunters needed expertise. The new stacking observers need discipline. Show up, record data, submit it. The network handles the rest. Democratization means lowering the skill barrier. More people participate. But the nature of participation changes. How many passed through the inner solar system before we had surveys capable of detecting them? How many will we miss in the next decade, despite better surveys? The answer, most of them. Space is big. Interstellar visitors move fast. Detection requires that the object passes through the small volume of space we monitor and happens to be bright enough to see. Most objects fail one or both criteria. We sample the brightest tip of the size distribution. 3. I-Atlas, possibly under 1 kilometer diameter, sits near our detection threshold. Objects 10 times smaller exist in larger numbers but remain invisible. Objects 100 times smaller are everywhere, passing through constantly, unseen. The ones we detect are not representative. They're the outliers, big enough or active enough to register. 3I Atlas became visible because it started venting gas early. If it had remained dormant, Atlas might have missed it entirely. The taxonomy of interstellar objects builds from biased samples. We know the bright ones. The faint majority remains unknown. This is the first interstellar object observed in detail by citizen scientists from backyard instruments. Oumuamua was already outbound when discovered, too faint for amateurs. Borisov was brighter, but still challenged small telescopes. 3I Atlas, discovered early, tracked continuously, arrived at the perfect time for the unistellar network to contribute meaningfully. 26 observers, 22 hours of continuous coverage, magnitude 17.8 detection. These numbers enter the history books. They mark the moment when distributed amateur astronomy achieved parity with some professional capabilities. Not all capabilities, but some. The ones that matter for time domain work and continuous monitoring. Professionals acknowledge this. The SETI Institute partnered with Unistellar specifically to enable these observations. The data goes into the same databases professional data uses. The citizen scientists get co-authorship credit on papers when their data contributes substantially. The relationship is mutualistic. Professionals gain observing capacity they cannot afford otherwise. Amateurs gain purpose and training they would lack otherwise. Science benefits from both. Tumbling, no coma, mysterious acceleration via outgassing that spectroscopy couldn't detect. Borisov looked like a solar system comet. Coma, tail, carbon monoxide rich, familiar chemistry. 3I Atlas looks like a comet but with exotic composition. Carbon dioxide dominated, nickel vapor. Early activity. Each object is different. If we saw 100 objects, would they cluster into types? Would we see a continuum? Would some be genuinely alien, made of materials rare in our solar system? The speculation is premature. 3 objects is not a data set. But the differences between the 3 suggest diversity. Planetary systems form under varying conditions, different stellar masses, different metallicities, different disk compositions. The comets ejected from those systems carry chemical signatures of their origins. We're sampling the galaxy's comet population. Each detection adds a data point. Eventually, the pattern will emerge. Maybe carbon dioxide enrichment is common in thick disk comets. Maybe nickel tetracarbonyl appears in systems with higher refractory element abundance. Maybe water-dominated comets like Borisov are typical, and carbon dioxide comets like 3I Atlas are rare. The answers wait in observations not yet made. Messier's visual observations in the 1700s, photography in the late 1800s, digital CCDs in the 1980s, automated surveys in the 2000s, stacking software in the 2010s. Each step expanded capability. The next step is already emerging. Machine learning applied to image classification, neural networks trained to recognize comets, asteroids, supernova, variable stars. Feed the network 1,000 training images. It learns the patterns. Then it processes new images automatically, flagging candidates for human review. The human review step might eventually become optional too. Fully automated discovery. No human in the loop until a confirmed detection requires follow-up decisions. This raises questions about the nature of discovery. If machine finds a comet and no human notices for a week, who discovered it? The machine, the programmer who wrote the algorithm, the institution that operates the survey? The answer depends on how you define discovery. Legally, the Minor Planet Center records the entity that first reports an object. Scientifically, discovery means characterizing the object enough to understand what it is. Culturally, discovery means the moment of realization that something new exists. These definitions diverge as automation increases. 3I Atlas was discovered when Atlas detected it, confirmed when follow-up observations verified the hyperbolic trajectory, and characterized when JWST revealed its composition. 3 separate moments, 3 separate groups. Who gets credit? Everyone. Astronomy is collaborative now. The lone wolf discoverer model belongs to history. Modern work requires teams, networks, and infrastructure. The credit spreads accordingly. 3I Atlas does this for stellar systems. The comet carries information from billions of years ago and trillions of kilometers away. Physical evidence of planet formation around a star we cannot identify in a region of the galaxy we can only estimate. The information sits in the ice. The isotopes, the volatiles, the dust grain composition. Each measurement extracts a datum. Stack enough data and a picture forms. Not complete, not perfect, but better than speculation, better than ignorance. The comet arrives from interstellar space carrying a message. The message is not for us. It was not sent. It simply exists. And we happen to be here with instruments capable of reading it when it passed through. Our solar system's carbon dioxide ice line sits around 6 to 10 AU depending on disk temperature. Other systems vary. A hotter disk pushes the line outward. A cooler disk pulls it inward. An older star with lower luminosity has a closer ice line. A young massive star has a distant ice line. 3. I Atlas formed somewhere in that parameter space. The thick disk membership suggests an old star, low mass, low luminosity, close ice lines. The comet might have formed at 3 AU from its star, or 30 AU. We cannot tell from current data. Future detections with better statistics might constrain formation distances using composition patterns. If all thick disk interstellar comets show carbon dioxide enrichment, that suggests something about thick disk protoplanetary disks generally. If thin disk comets show different compositions, that suggests evolution in disk chemistry over galactic history. The clues accumulate slowly. Astronomy is patient work. Magnitude 10.5, visible in 6-inch telescopes, clear in 10-inch instruments. The comet moves outbound, growing fainter. Activity declining as solar heating decreases. By January, it will be magnitude 12. February, magnitude 14. March, magnitude 16. Each month it fades. Each month the required aperture and integration time grow. Eventually it becomes accessible only to Hubble and JWST, then only to JWST, then not even that. The light travel time increases. The comet recedes. The data flow stops. Unless the comet does something unexpected. Outburst, fragmentation. Comet's surprise. 3I Atlas might brighten suddenly if buried volatiles vent explosively, or it might simply fade into darkness. The uncertainty is intrinsic. Comets are dynamic objects. Predictions are educated guesses. Observations are ground truth. We will see what we see when we see it. The most sophisticated models cannot account for every variable. Nature always has another trick. Comet scientists know this. They watch and hope for surprises. Nucleus possibly detected directly. Size measurement, shape estimate, the carbon dioxide to water ratio measured again. If it stays 8 to 1, the nucleus is intrinsically rich. If it drops toward 4 to 1 or 2 to 1, the thermal explanation holds. If it rises to 10 to 1 or higher, outgassing dynamics are more complex than models predict. The measurement will take hours. Telescope time is expensive. Proposal competition is fierce. But 3I Atlas earned its time. Third interstellar object. Unique composition, one-time opportunity. JWST will observe, the data will process, the papers will publish. And years later, when someone stacks all observations from all wavelengths into a comprehensive dataset, 3i Atlas will sit in archives as a complete record of an interstellar comet passing through. Future astronomers will mine that data for questions we haven't thought to ask yet. The investment in observation today pays dividends in knowledge tomorrow. This is why we build telescopes. This is why we process data. This is why stacking beats visual hunting. We're not collecting images. We're collecting the future.